All right, so in Chapter 8, Section 2, we're going to analyze some of the other trigonometric functions, aka not sine and cosine. So let's start by taking a look at the tangent function. So recall that tangent can be defined as sine x over cosine x. And we know that both sine and cosine have a period of 2 pi. So let's go ahead and plot tangent on 0 to 2 pi and see what it's going to look like. So let's go ahead and generate this table on our calculator. So if we go into our y equals, I'm going to do sine, I'm going to do cosine. I mean, we could just directly do tangent, but then I'm going to do y3 as y1 divided by y2. And hit enter. I'm going to make sure my calculator is in radians, which it is. So then if I go to my table, I have my x's and my y's. So the first column now let's change this. The first column is my x's. So we're going to go second table set. We're going to go down here and change it from auto to ask. So now when we go second table, it's going to ask us to actually input the values we want to calculate. So we're going to put in 0, and we're going to do pi over 6, and we're going to do pi over 4, pi over 3, pi over 2, and then the next one is 2 pi over 3, and we'll go 5 pi over 6. Alright, and that gives me one full screen. And scroll over, there's our y3s, which is the actual values of tangent that we wanted to calculate. So that gives us our first chunk for our tangent. We get 0, 0.55, pi over 4, which I didn't put in the table. That's terrible. So this one is pi over 4. We're going to get these values. And let's keep going. So to speed up our process now, let's just go ahead and put our table on auto, or not auto, on ask, but get rid of all of this and just calculate the tangent directly. So if we just go tan and x, oops, Didn't want a graph, but that's okay. Table. So we'll notice we do get the same values that we were getting here. And if we scroll down a little bit more, we see we got our first negative value in our table. So we can keep adding some more values. So let's go with 2 pi over 3. 5 pi over 6, and pi. And we notice something interesting starts to happen. 7 pi divided by 6, 4 pi divided by 3, and 3 pi divided by 2. We get another error. So something interesting started happening as we generated those values. So as we started to graph our function, let's go back to our table set. Let's have our table start at 0. Oh, this needs to be pi divided by 6. We'll put it on auto. And now if we go second table, we get the following set of values. Yeah, 0, 0, half, pi over 3 is going to be 1.7, and pi over 2, we got an error. And then our graph, we started getting some of these same values again. But the negative type. So here, here, and if we scroll down in our table, we notice the exact same thing seems to happen again. So we get back to 0. And then we get another error. And if we keep going, we're going to notice the same thing seems to be happening. So we might guess, based on this, we see our graph repeats. So it looks like this is going to be one period of our graph. So from pi over 2 to 3 pi over 2. So that means here it would be from negative pi over 2 to pi over 2. Which means our graph would have some symmetry with respect to those. It would look something like this. And we could keep extending copies of our graph in both directions. So the first thing we note, based on this, the period of tangent is pi, not 2 pi. So sine and cosine both have a period of 2 pi. Tangent, which is the ratio of sine to cosine, has a period of pi. So we have the following properties which are going to hold for tangent. So the function f of x equals a times tangent bx has the following properties. A is our stretching factor, so since it's not a periodic wave, we don't call it the amplitude. The period is p equals pi divided by b. So notice the difference in this formula is that it's not 2 pi because our period's not 2 pi, our period's pi. So it's pi divided by b. The domain is x such that x is not equal to pi divided by 2 absolute value b plus pi bk for k any integer. Its range goes from negative infinity to positive infinity, and it has vertical asymptotes at all of these points. So one thing that's worth noting is these are the zeros of cosine. So why is it that that would be the zeros of the cosine function? Well, it's because tangent is sine x over cosine x. So we're going to have a vertical asymptote when cosine is 0. And the tangent function is an odd function, as we saw in the graph above. All right, so let's sketch a graph of one period of this function, 2 times the tangent of 3x. So we have our a, so it's going to stretch by a factor of 2, and our period is given by this formula, pi divided by b. So our b is going to be 3, so the period is pi divided by 3, which is going to be just pi over 3. So going back to look at our graph, our period used to go from pi over 2, or negative pi over 2, to positive pi over 2. Well, if our entire period is pi over 3, that means it's going to go from where to where. So here, my period was pi, and it went from negative pi over 2 to positive pi over 2. So if our period is this, we're going to divide it by 2. So we're going to go from pi over 6 half a period is pi over 3 over 2, which we can make a fraction over 1, which is pi over 3 times 1/2 is pi over 6. Pi over 6 is just a little bit bigger than a half. So our period is going to go from negative pi over 6 to positive pi over 6. So our graph can be super skinny and look something like that. I ran over my asymptote, but that's okay. All right, example 2. Sketch a graph of one period of the function negative tangent pi x plus pi plus 1. So we're going to want to do the same type of analysis, and then we'll sketch our graph. So we identify our a this time as -1. So this is going to be no stretch, but reflects across the x-axis. And then we've got this going on in here. So we have pi x plus pi, which can be factored into pi times x plus 1. So this is going to be for our period. Is pi divided by b, which in this case is pi divided by pi. So our period is going to be 1. This piece right here is a horizontal shift. And it's going to be 1 unit left. Lastly, we got this guy right here, and it's going to shift up 1 unit. All right, so now we have all of that. Let's grab our graph. And we're going to draw our picture. So our period's 1 unit, which means we're going to have our vertical asymptotes at a half. So we're not going to stretch, but we're going to reflect across the x-axis. We're going to shift 1 unit left. Our period is 1, and we're going to shift up 1 unit. So normally, the generic tangent goes through 0, 0, and looks like this. So now we're going to need to do all of these things. So this is our parent function, y equals tan x. So we need to reflect it across the x-axis, shift it left 1 unit. We've already got our period taken care of. So just kidding. This is actually the tangent of pi x, because we made the period 1 already, and then we need to shift vertically 1 unit. So we're going to flip it over. We're going to move it left, and we're going to move it up. So we move it left 1, up 1, and flip it over. So our graph is going to look like that. That would be 1 period, and then you could just copy the periods. But in the instructions, we were only asked to graph 1 period. So the graph in green would be the actual function we were asked to graph. All right, continuing. Find a formula for the function in the graph. Okay, so we've got our vertical asymptotes, and we've got our function looking something like this. So our period is going to be 4, and it doesn't look like we have any vertical or horizontal shifting. So it contains the point 0, 0, so that tells us no horizontal or vertical shifts. So if our period is 4, our formula for the period is P is equal to pi divided by B. So that would give us 4 is equal to pi over B. So solving for B, we get 4B is equal to pi, divide by 4, divide by 4, and we get B is equal to pi over 4. So if B is equal to pi over 4, we get y is equal to the tangent of pi over 4x. So the next question we want to ask is, how can we use the graph of sine and cosecant, or sine and cosine, to graph secant and cosecant? Well, the key here is the reciprocal identity. Because we know, by definition, that secant x is equal to 1 over cosine x. Well, that would mean that they are reciprocals of each other. So right here we have a graph of the cosine function. So if I had a table of values for cosine, the secant would be 1 over that. Well, what's the y value right here? Well, 0, 1. The reciprocal of 1 is 1. So we get this same point. And if I go check my unit circle for a couple of these values, we'll notice cosine is x. So then cosine at pi over 3, which is just bigger than 1, would have a value of 1/2. So if I look at that on my graph, so pi over 3 is a little bigger than 1, so that's right here. So at pi over 3, I'm going to have a value of 1/2. Well, what's the reciprocal of 1/2? 2. So this graph has to have the point pi over 3 and 2. At the point where we cross the x-axis, which is cosine is equal to 0 at pi over 2, well, then I would be dividing by 0, because the reciprocal of 0 is undefined. So that tells me that that's going to be a vertical asymptote. So in fact, all of the zeros, or x-intercepts of cosine, are going to be vertical asymptotes of secant. So I get something that looks like this, and if I keep doing these reciprocal values, so I start going here, I'll notice that I get the same bounce back out here. I get a half again, so it's going to be up here. So this guy is going to look like this. Similarly, it's going to look about the same here, except for all of my values are going to be negative. So the reciprocal functions look kind of interesting in the sense they're going to look kind of like this. They're going to be equal to each other at the points where they're 1, because the reciprocal of 1 is 1. Because if you flip over 1 over 1, we're going to get 1. And we get these asymptotes for secant are everywhere cosine is 0, so all of its x-intercepts. And that gives us kind of a fun looking graph. All right, it's your guys' turn. So go ahead and draw a graph of the cosecant function and identify its vertical asymptotes. Remember, cosecant by definition is 1 over sine. And this is a graph of the sine function. So use that graph to draw a graph of the cosecant function. All right, so our vertical asymptotes are going to be anywhere sine is 0. So sine of 0 is 0. Sine of pi, and then 2 pi, and so forth. We'll get some over here as well. Negative pi, and then doing the same thing, our graphs are really going to look something like this. So that's going to be the graph of our cosecant function. So one thing that's worth noting is, once again, the period of each of these is pi, and if we look at our previous graph, we'll see the same thing. Now, our period was from pi over 2 to negative pi over 2, so this is our period once again, and it's going to be pi. So on both of those functions, we got our period as pi. So we want to determine the stretching factor, the period, and the phase shift of 3 cotangent 4 pi. And we have our A, and we have our B. So our stretch factor is 4, and our period is equal to pi divided by b, which is 4, so it's going to be pi over 4. Since we're not subtracting, c equals 0, so no phase shift. And that would be our our stretch factor, our period, and our phase shift.